Hi, this is Stephen Brower from Raton Valley Community College. This is part 2 of the remove. In part 1, we took a look at the loop, which moves cursor and parent of cursor down the tree. And we have to move cursor either to the left or to the right. And it referred back to the exists method. And what I did in the part 1 video is I went through a couple examples. So for trying to remove kumquat for the loop, cursor fell off the tree. For this one right here, cursor was at root. This one right here, cursor is at raspberry. This one right here, cursor is at cantaloupe. And then going through the first 2 conditions here, the first condition here, when cursor is null, and I mentioned that the reason why this if statement is done is so that here when we're comparing cursor and looking at cursor get left, we're not going to get in the NetBeans a warning message saying that, hey, this might be null. We could get a null pointer exception. So this condition 3, cursor is not at the root and there's no left child. So here we're at raspberry. So cursor is not at the root. Cursor is not at the root and there's no left child. There's nothing to the left of raspberry. Now, let me take this pseudo and let's Javasize it. So if cursor is not at root and cursor.get left is null. So remember, this is going to be a long else if chain with a trailing else at the very end. If the cursor is not at the root and the cursor get left is null, then we want to take the parent link and set it to the right of cursor. Well, in this one right here, in other words, cursor here, this is the node we want to remove. And so what we want to do is take the parent. In this case, we particularly want to take the left, and we want to change it to say that it's now going to be to the right of cursor because there's something there. So this if statement is inside, meaning inside of this. So if this is an open curly brace, then when it says here take one of, we have to have the if. So if cursor, well, cursor here equals parent get left. Well, parent get left is here. They're the same. So parent set left, we're going to be changing this pointer to cursor get right. Well, cursor get right is there. And so that now will have tangerine point to strawberry. And it's maintaining the search tree order. I'm sorry, maintaining the order because the ST strawberry is before tangerine, so we're maintaining search tree order. What I will do is, let me just pull these out of the way. I'm just moving them off screen for a second, and then just logically, then the tangerine is now pointing to the strawberry. Okay, so that was within condition 3. So if the cursor is not at the root and the cursor has no left child, then we're going to take one of the parent's pointers. In this case, we're going to say, well, if the cursor equals parent get left, which it was, parent set left is cursor get right. So tangerine, the left of it was then pointing to the right of what was pointing to the right of raspberry. What this set of slides doesn't have, but if you look back at my slides online, that I have the other condition here. So this is the first condition, in this case removing 5. And so that's where the parent set left, cursor get right. But this example here was showing, so if 21 is being removed and there's no left child, of it, then it's actually going to be parent set right, cursor get right. So this else here that's on these slides is the else that would correspond with this condition here. But so condition 3, we weren't at the root and didn't have a left child. So then the final thing, the trailing else, so else, I'll do curly brace, we're going to have the block of code here, and it says go into the left subtree and find the rightmost child, bring that to the cursor's data, then remove that rightmost child in the left subtree. What? Okay, so the condition we have, when we get down to here, well, we're going through the conditions. So the first condition, if cursor is null, cursor is not null, so it's not that condition. The second one is if cursor is root, well, cursor isn't root. The third condition is if cursor is not root, which cursor is not root, and there's no left child, well, there is a left child. So this fourth condition here we're dealing with, we know we have a left child. So the idea is the subtree to the left, all of these items are less than cantaloupe, but the largest value on the left-hand side is blueberry. And the way we find it is from cantaloupe, if we go left and then keep going to the right till we can't go right no more, that is the largest value in the subtree that's to the left of cantaloupe. So we're going to the left and we're keep going right until we can't go right no more. So there is a two algorithms that will help us with this. One is the get rightmost data. And so what the get rightmost data does, it keeps going to the right till we can't go right no more, and it will return the value. So basically, it's kind of like looking at a node. When we're looking at this node, we want to return the rightmost data. Well, since right is not null, we're going to turn to the right-hand side and say, hey, give us the rightmost data. So then we come here, and it's going to say, well, is the right null? Oh, the right is null. Hey, on the rightmost data, it's going to return itself. It'll return its value. So what we want to do is cursor set data. We're going to change the value here to blueberry. And so the cursor set data, we're actually changing the value in this. So at the present moment, after this first statement is done, we actually do have a duplicate at this point. Now, this next piece is going to be weird. If you notice the first part, cursor set left. So what we're doing is we're rebuilding the subtree on the left-hand side. And so in a sense, what we're doing is we're going to say, okay, let's now make the subtree on the left one in which the rightmost node has been removed. And so blueberry is talking to banana, so cursor get left, and saying, remove your rightmost item. And then, because we're going to be assigning it, then return to me the root of the subtree who's had its rightmost value removed. And so the banana is looking at himself and saying, well, there is something to the right. So let me ask it to remove its rightmost. So banana then asks blueberry to remove the rightmost, and then say, return to me a tree where it had the rightmost removed. Then we get to blueberry. And then blueberry looks right and realizes there's nothing to the right. And it's like, oh, crap, I'm the one that's being removed. And so what it'll do is it will return left. So what blueberry will bring up to banana, blueberry will bring up to it the value that's to its left, which is blackberry. And so logically what happens is blueberry disappears and blackberry is being returned to the right of banana. So blackberry, so this node is now going to banana and saying, okay, I am in the subtree that had the rightmost removed, and then banana is going to return to blueberry. Here I am one that had the rightmost removed. So the net effect of this line here, cursor set left, cursor get left, remove rightmost, is that the rightmost node was removed. In that case, it was the blueberry. So we no longer have the duplicate that we did after the first one was done, and that value is removed. And so that last condition is we're going into the left subtree and getting the rightmost value. So for example, suppose plum is one that we would remove. And let me just give this a different color for right this moment. But suppose plum is one that we wanted to remove. And so suppose cursor was pointing here to plum. So suppose, sorry, I hate technology. Suppose plum is the one that we want to remove. So what we would do is cursor set data, cursor get left, so we'll go to the left subtree, get the rightmost, which is pair. So then the value pair would come up here. So that first line will copy the data from the rightmost on the left subtree up to here. And then what we're going to do is change this link to basically we're going to turn to orange and say, give me a subtree, or re-give yourself to me. That sounds bad. A subtree that has had the rightmost removed. Well, orange looks right and realizes there's something, so it turns to pair and says, give me something with the rightmost removed. Pair looks right and realizes, oh crap, there is nothing to my right. I'm the one that has to be removed. And so it returns left. So what it will do is it returns peach as being, here is a subtree of me that has had the rightmost removed, which is returning it to orange. And so orange is returning itself to pair and saying, here we have a tree with the rightmost removed. So the gist in condition 4, we have a left child, we go into the left subtree, and we get the rightmost value for doing a remove. Okay, so a recap. The remove, there's two pieces to the method. It's a long method. The first piece is the loop, and the loop that is here is very similar to the exists in terms of moving cursor down, and then after the loop, so after the while, then that's where we have this long else if chain. So if cursor is null, we return false, or say found is false. Else, if cursor is the root and cursor does not have a left, we do root equal root get child. Else, if cursor is not the root and cursor get left is null, then we take one of the parent links, so either parent set left or parent set right, and we set it to cursor get right. And then otherwise, we're at the point where we have a left child, we go into the left subtree and we copy the data that's at the rightmost part, so it's the largest value in the left subtree, and then we go and we remove that node, that largest one that's at the end. Again, there are 200 to 300 algorithms for remove. This is just one of them. So if you pick up a different book, you will see something different. This matches the several pages of text that the author has written on the algorithm. And so I'm just taking the algorithm that he described and putting pseudocode with a little bit of Java to it. There are gaps in this, meaning that, for example, condition 2, we could have said, well, if the cursor is the root and cursor get right is null, we could have done root equal root get left. This doesn't have a scenario. That would actually fall under condition 4 in this. So it is a simplistic algorithm. But here's the other thing. The more conditions we have here, the more tests we're going to have. When you see Lab 7 Part B, you're going to see that we have to have a test for this. We have to have a test for this. We have to have 2 tests for this. We have to have a test for this. We're going to have a lot of test conditions. There's going to be multiple test files. It'll help us narrow down where the issues are. Okay, so we try to find what we want to remove, and then we remove it.